Let's take a look into this example now. We would like to have a half-band low-pass filter. So this means that we would like to have a pass band from frequency 0 up to the frequency pi divided by 2. So this is a half-band filter. If we want to use it for sampling rate conversion with a downsampling factor of 2, we actually need to make sure that the stop band starts at pi divided by 2. We also need to create a transition band, for instance, from going from pi divided by 2 minus 0.1 to pi divided by 2. So this transition band is where we don't care about the value of our frequency response, and it's something that we can use to fine-tune the resulting filter. So for instance, if we see we don't get enough attenuation, we can increase the bandwidth of our transition band. Here our pass band is given as between 0 and pi divided by 2 minus 0.1. So we having this transition band, yeah, and we have our pass band from 0 to pi divided by 2 minus 0.1. This is still not an ideal filter. Yeah? So we can also define an error measure or an error function which measures how close we come to the ideal, so how good the filter is, which we can use to obtain a design minimizing this error function. So the often used error functions are the mean squared error, the mean absolute error, the weighted mean squared error, or the minimax error function. So this minimax error function seeks to minimize the maximum deviation to the ideal. So the weighted mean squared error uses weights to give errors in different frequency regions with different importance. So for instance, the error in the stop band is often more important than in the pass band to obtain a high attenuation in the stop band. So an error of 0.1 in the pass band might not be so bad, but an error of 0.1 in the stop band leads to perhaps only minus 20 dB attenuation, which is not very much. We optimize in the linear domain and not in the dB domain. So in this case, we might assign a weight of 1 to the pass bands and a weight of 1000 to the stop bands to obtain higher stop band attenuations. So the optimization usually results in the same or similar weighted error for all frequencies. So for FIR linear phase filters, Python has a specialized optimization in the function remes. So it's from the SciPy signal libraries, which implements the so-called Parkes-McClellan algorithm using the Chebyshev algorithm. So you can also take a look at the discrete time signal processing book from Oppenheim, and you can see some description about this algorithm. So now we can have a little example using this minimax error function. So the algorithm minimizes the maximum error in the pass band and the stop band, weighted in comparison between the two, which leads to a so-called equiripple behavior. So all ripples have the same height in the same band, so in the stop band or the pass band of the filter in the frequency domain. So we can take a look at the remes function for SciPy signal. So we can see here, this is the help. So this is how the function looks like and all the possible arguments. So this function calculates the minimax optimal filter using the remes exchange algorithm. So it calculates the filter coefficients for the finite impulse response filter, whose transfer function minimizes the maximum error between the desired gain and the realized gain in the specified frequency bands using the remes exchange algorithm. So it has the parameters. So num taps is the desired number of taps in the filter. So this is the filter order plus 1. The bands, so it's a monotonic sequence containing the band edges, so all elements must be non-negative and less than half the sampling frequency as given by Fs. So this is the desired argument. So this is the sequence, half the size of bands containing the desired gain in each of the specified bands. Then we have the weight, so it's a relative weighting to give to each band region. So the length of weight has to be half the length of the bands. Then there are some other parameters, so we can set which kind of filter. If your type of filter is a band pass, so it's a flat response in bands, this is the default. It can be a differentiator, so the frequency proportional response in bands, or Hilbert, this filter with odd symmetry, so it's a type 3 or type 4 for odd order, or type 3 for even orders. So you can take a look how to use some examples here, and we will use this function in our example.